lab that you're going to do today is we're going to attempt to find the moment of inertia of a spinning disk, right? Now, moment of inertia is hugely important, but here's the anomaly about moment of inertia, is that we don't have moment of inertia devices. It is like, hey, Burkamp, can you get me the moment of inertia detector that we can run with lab pros? It's like, they don't exist. So what we have to do is kind of get clever and find an indirect way to measure the moment of inertia. So here's what you're going to do. So if you look on the lab, and I'm just going to kind of show you the heart and soul of this thing right quick. So over there on page 2, basically I'm going to divide you up into like 2 groups. There's going to be a group that does the small pulley and a group that does the large pulleys. So,
Big.
Okay, fine. So on the small pulley, and I've given you the radius, you're going to attach a 20-gram mass, and you're going to wind this thing up, and then you're going to let it fall. Okay? Now, here's the question. When I let go of this thing, is there linear acceleration of the 20-gram mass?
Yes.
Yes, very much so. What's pulling it down?
Gravity.
Gravity. Okay, so gravity's pulling that down. If gravity's pulling it down, though, why doesn't it fall at 9.8 meters per second squared?
Because it's got to accelerate that wheel too.
So, is there tension acting up?
Yes.
Tension is going to be a key part of this story, because it's the tension here that's making this accelerate. Now, here's the story. Does this undergo angular acceleration?
Yes.
Yes. If it didn't, it would just sit there. Okay? So we have, this is unique because you're going to have 2 different accelerations. You're going to have the acceleration of this, and you're going to have the angular acceleration of this. Now, which one do you think is going to be easier to measure? The linear acceleration of a falling mass or the angular acceleration of a spinning wheel?
Linear
Linear acceleration of falling
Beautiful.
mass.
Why? Because there are only 2 things you need to know. You've done this calculation 20 times.
Time and distance.
I need time and distance. Okay? Easily done, right? So I can sit here and go, okay, I'm going to wheel this thing up. I'm going to set a meter stick, and I'm going to let this thing fall a certain distance. And then I'm going to time it. Boom, let it go. Maybe 40 centimeters. That's when I did the lab, I set it at 40 centimeters. You can set it at whatever you want, okay? Obviously, don't do 1 centimeter. That's going to be tough to do. So you're going to do this, and you're going to do this with 4 trials. Now, once you get that done, now keep in mind this visual. See this? Boom. Have a certain acceleration. Got the visual.
Yep.
Now, I'm going to take off the 20, and then I'm going to put a 50-gram mass on the end of it. So now what's going to happen to the acceleration?
It's going to be
bigger.
greater.
Bigger?
Yes.
Yeah.
Quite
Why?
bigger.
Because
Because
more force. Because
More
more
force.
mass.
Gravity.
And
Right?
gravity pulls harder.
So it pulls harder, so therefore I should get
More acceleration.
more acceleration. But no matter what, is my linear acceleration, is it going to be bigger or smaller than 9.8 meters per second squared?
Smaller.
Smaller, because I have tension acting up, gravity acting down. This is going to be important. Tension is always going to be acting up, or at least in the opposite direction of this as it falls. Got that? Okay. So if you're on the small group, that's what you're going to do. You're going to hook that up. Boom. There you go. Then the only thing that changes is if you're Cohen and you want to do the big pulley.
Yay.
Okay?
Big
So it's the
pulley,
same
particularly.
idea, but now, listen to me very carefully with this one. So with this one, you're still going to do, it's the same idea, but the masses are going to be different. Yes, I said the D word, but it's relevant to this discussion. So what you're going to do here, now you're going to use 10 and 20. Okay, so you're going to use 20 and 50 on the small, and you're going to use 10
Oh, because it's tangential, so it should.
Okay? Now, so if you kind of remember the visual
Tangential on this
of what
one.
happened when I had the 20-gram mass pulling on that one. So now I want to do this one. Okay? So, and especially if you compare a 20 to a 20. So if I put that 20-gram mass on this one, okay? So if you kind of remember the visual of how slow it fell when it was on the small one, now what's going to happen to this one?
Way faster.
Very fast.
Very fast. Okay? If you've got the big one, which is what you asked for, that's the most difficult one because it falls so fast. So you
Right.
better have your timing A game.
I'm crazy at timing.
Okay,
Yeah, we trust Will.
mad skills.
Danny,
My
you have to go to May South Street this time.
Okay,
my stopwatch skills.
so,
We're making you a
but it's,
dishonorary.
you're gonna do the same idea. So this is why I said the data collection portion of this goes pretty fast, all right? So you've either got the small pulley, you're gonna use 20 and 50, or you've got the big pulley and you're gonna use 10 and 20. So the reason that I don't put the 50-gram mass on the end, why don't you think I use the 50-gram mass?
That'd be insanely
It
fast.
falls
Yeah,
so fast.
it's gonna be insanely fast. So that's why I use the 20 and the 50 on the small and the 10 and the 20 on the outside. Okay,
Throw the 1
now,
kilogram mass on there.
It'd be like driving it.
now I'm gonna take you through the math, okay? I do this, but I'm also gonna I lay it out in the instructions, but I'm also gonna take you through a set of calculations. So here's the basic idea. And this is what's on the front of the lab. So here's this wheel, and you have this string attached to it. Why isn't this thing drawn today? So I've got gravity pulling it down, and I have tension acting upward. Now, this is going to be important when you get to a big complex question on the back of the lab. It's a simple idea, but it's going to be important. If that thing falls, which it does, which is bigger, the gravitational force acting down or the tension in the string pulling up?
Gravitational.
Same.
Oh, it's same. No, gravitational force going down
Why?
because it accelerates downward.
Because it accelerates downward.
Yeah.
If it was the same, then they wouldn't move.
Yeah, if the two
Oh,
values
yeah.
were the exact same, nothing would happen. Okay? So what's happening is that tension is making this thing spin. Okay? Got that idea? Now, on the problem on the back, when you get to it, you'll see that that actually has two masses. And that is a complex problem. With that one of the masses actually goes up and one goes down. So if that situation where the mass goes up, the tension in the string is bigger than the gravitational force acting downward. But on the one that falls, the gravitational force acting down is bigger than the tension acting up. Okay, we'll get to that problem later, but I just want to point that out. So here's the story. So what you're going to do is that, for example, when I did my small pulley, and this is just to give you a reference, okay? My time was about 1 second to fall 0.4 meters, okay? That was just kind of a ballpark. So what you want to find is the average linear acceleration. So when I did it, I let it fall 0.4 meters. If you're clever, and you are, what are you going to let the initial velocity equal?
Zero.
Zero.
We're gonna
And
throw it at the
x equals 1/2 at squared. So you're going to know how far it's going to fall. You're going to use your average time. You only have to do this one time. Now, for trial 1 on that small pulley, I don't need to see all the calculations for all 4 trials. But if you notice on page 2, I've got big boxes down below. I want to see that set of calculations for trial 1. Okay? I don't have to see them for the other ones because it's you're going to have the idea by then. But on trial 1, I want to see a complete set of calculations. So what I want to see there is that you're going to go, oh, 2x over t squared, that's going to give me the linear acceleration of the falling mass. Cool, right? Now, we need to talk net force. So we've got tension acting up, right? And we've got gravity pulling down. So here's the idea. So if you look at terms of net force, and remember net force equals what? The basic idea, the simplest way to do net force. Simplest way to calculate net force is the
MA.
big red sign.
MA.
Mass times acceleration, right?
Ma.
Okay. Now, that's going to
Put a lot of
equal
force
the
in your
difference between the gravitational force and the tension, right? Okay? And your gravitational force is bigger. That's why it falls. So at this point, you're going to know MA, because you're going to know the mass that's falling, and then you're going to know that acceleration. So you're going to have the value of the net force. You know how to calculate FG, so what we need to do is solve this for tension. So if I move this tension over here, and I move that over there, then I've got MA, or MG, minus MA. So now, if I factor out a mass, I've got G minus A. So, here's the story. Now think this through. What if you just cut the string?
It'd fall at 9.8 meters per second squared.
Your acceleration would be 9.8 meters per second squared. And what would you get for the tension in the string?
0.
0. Now, if you have no acceleration and you're just holding it, what's the tension in the string?
Equal to the
Equal to the
force.
weight.
Yeah.
So this equation works on both circumstances. So it works if you just cut the string and you get no tension. Now, but here's the trend. As this acceleration gets bigger, okay,
Tension gets smaller.
tension gets smaller, okay, which seems a little bit counterintuitive, okay? But what's happening is that that increased tension is working more to spin the wheel, okay? Now, so that tension column, you're going to use this, m times g minus a. At this point, you're going to have the acceleration. Now, on the torque column, and don't confuse tension with torque, okay? Torque is technically the Greek letter tau. So this one, you're just going to use force times radius. So what's creating the force to make the wheel spin?
Gravity.
No.
Damn it.
Rhymes with engine.
Tension.
Yes, because if I don't have any tension on the string, guess what?
It won't.
Nothing
It
happens.
won't spin. So this force is going to be the tension that you just found up there. Okay? So the torque calculation is the tension. This is why this goes very sequentially. So basically, we want to take this thing step by step by step. So the torque calculation becomes the tension times the radius. And you have the radius. Cool. Okay? Now, your angular acceleration. Well, A equals R alpha. Do you have your angular acceleration?
Yeah.
Nope.
No. No, we don't. We have normal
But do
acceleration.
you have your linear acceleration?
Yes.
Do you know the radius of the object?
Yes.
Yes.
Yes. So you can find alpha by doing what?
Dividing
A over
over
R
R.
equals fish.
R equals fish. R. Fish.
Okay.
Sorry.
Now,
Pirate.
torque equals two things. What
Stab one
are the
right
two things that torque equals?
The I, but, and
I fish.
How about I fish?
yeah, I fish. Sorry,
and-
wrong one.
And
FR.
force times radius, right? So here's the story. At this point, you know what the torque is. You found it. You know what the torque is. You just calculated the angular acceleration. So how are you going to get your moment of inertia?
I am torque over fish.
Yeah, take the torque, divide it by
I is torque
the
over
fish,
I is
and there's your value of I.
Bro, physics math is so whack once you start reading
Now.
the
These moments of inertia, because these are
it's
very
perfect.
small masses, okay, and you're not dealing with big radii. Typically, as a ballpark, your moments of inertia are typically in the high negative fifths or low negative fourths. Okay? Typically, that's where those moment of inertia should end up. Like maybe 9 times 10 to the negative fifth, or like 1 times 10 to the negative fourth. Kind of in that same ballpark. So, what you need to do very quickly is that you need to get data. Okay? And that's why I said I want to divide and conquer. I want one group doing the small pulleys, one group doing the big pulleys. We'll put the data on the backboard, and then we're just going to swap data. Okay? Ready?
Yep.
Great. Stop.
Bye, Colin.